All right, still looking at rates of change. Now, probably the most, I don't know if common's the right word, but the most useful rate of change when it comes to calculus is for describing motion. And in fact, that's the whole reason calculus was started in the first place, is when they were trying to work out planetary motion. And calculus came about because of that. You've actually been studying motion since, well, when did you first look at travel graphs? Year 7, year 8, something like that? Maybe even in primary school you might have looked at some. But travel graphs are a way of investigating motion. The big difference is, you might remember the ones in year 7, year 8, they're always usually just made up of straight lines. Motion doesn't have to be a straight line, of course. So a ball is bounced and its distance from the ground is graphed. So I've still got a travel graph. Distance versus time. But I don't get those nice, neat straight lines. We actually end up with a parabola when a ball is bounced. Now, all the rules still apply that applied before. We know at the top is when it stops. If you go back to a travel graph, you might remember you looked at it and you went, and they asked you a question like, Fred and Jim were going on a road trip. They stopped for a picnic. What time did they stop? And you looked for the horizontal line and you went, oh, look there, because they're not moving. Well, what you actually have just found, if you like, is the stationary point. It's when the tangent is horizontal. Same deal. No different. Except the difference here is it only stops instantaneously. You think about bouncing a ball, bing, it goes up, it goes down. But there must be an instant there where it stops. That point where it stops going up, starts coming down. But you can't change direction without stopping. And so we can combine our ideas with calculus to investigate the motion. So there's the equation of this particular travel graph. Now, some terms. Distance, of course, is the total amount travelled. Displacement is simply how far from the starting point. So there's a big difference. Distance is total amount travelled, whereas displacement is just, okay, how far have I ended up going from the starting point, if you like. So, questions like this. Find the height of the ball after 1 second. Well, we've got a formula there we can sub into. And we say, oh, righto, we're 35 metres up in the air. So what other times is the ball at the same height? Yeah, we could read off the graph, or we could simply solve the equation. We want to know when x is 35, we end up with a quadratic. We already know one of the answers. It's t minus 1, t minus 7. So, well, 1 was the first time, that's when it was going up. 7 must be when it's coming back down. So, okay, after 7 seconds. Average velocity is the change in displacement over the change in time. Now, because you're used to probably dealing with speed, and we say speed is distance over time. It's basically the same formula. The difference, and we'll see this in a sec, the difference between, say, displacement and distance is just magnitude. It has no direction. Displacement actually has direction attached to it. And so speed goes with distance, because speed also has no direction attached to it, whereas velocity does. So velocity, instead of distance over time, is displacement over time. And that looks really familiar when you look at that little formula there. x2 minus x1 over t2 minus t1. Remember we had an x-axis, which was vertical, a t-axis, which was horizontal. What's the other formula for?
Gradient.
Gradient. So there again, the slope of the tangent will be velocity. At an instant. See, average is over a period of time. But if I found just a tangent, I'd find it at that instant. And that's more useful. All right, we're going to find the average velocity during the first second. So after 1 second, we said it had gone 35, and obviously it started at 0, and change in time is 1. So the average velocity, no surprise there, in the first second it travelled 35 metres, so it was travelling 35 metres per second. Not a huge surprise there. Now if I want to find it during the 5th second, so the 5th second would go from 4 to 5. So at 4 it's 80, at 5 it's 75, so it must be on its way back down. So the average velocity is -5. So that negative we now has meaning, it's direction. And that negative in this case means it's going down. It's going in the opposite direction. So the average velocity is -5 metres over that particular second. Okay, during the whole 8 seconds, well, it started at 0, it finished at 0. 0 divided by 8 is 0. So the average velocity was 0. It didn't move. Huh? Well, yeah, I suppose that's right, because here I am, I go and do whatever I do, but then I finish and I'm back in the same spot, like I never moved. So the average velocity was 0. But that's why average velocity probably isn't that useful. We're more interested, as I said before, in instantaneous velocity. Anyway, average speed, as I was saying, the difference of speed is when we do distance divided by time. We're not interested in the direction. So average speed during the 8 seconds, because I did actually travel that, well, the ball did, it went up and down. So the total distance it travelled was 160. It went 80 up, it went 80 down. So in that 8 seconds, so the actual average speed was 20 metres per second.